All right, so welcome to the last section of video for chapter 2. There's an application section after that, which is applying everything we've already done. So this last section uses the chain rule. It honestly uses all of our previous rules, but the chain rule is the biggest one we'll look at. So up until this point, we've always done explicit equations. So they're f of x equals y. We have all of our x's on one side, or we can put them all on one side easier. We have all of our y's on the other, and we take our derivative. At this point, we're going to use implicit. So you have a function of f and y. I wrote this as alpha equals f of y of x. So a function of two variables where alpha is a real number. We call our functions implicit when we can't separate out the x's and y's easily, or we have an x times y. Now, for the function I wrote down here, we could easily separate them out, solve for y, and actually we're going to do that. But some of our other ones, so say I had y squared plus y minus x equals 18. We can't solve that for y easily. So this is where we use implicit differentiation. And honestly, it's one extra step from what we've done before. So it shouldn't be terrible compared to, some of the other things we've done, but these should all be pretty straightforward. So first example is we're going to find the derivative of xy equals 1 using explicit differentiation. Oh, whoops. So solve that for y, not for x. I get y equals 1 over x, which I prefer to write as x to the negative 1. So just divide both sides by x. And now we differentiate. So dy dx equals, all right, we have a power rule. Yeah, power rule formula. So bring our negative 1 in front. I get negative x. Subtract 1 from the exponent to the negative 2, which I can write as negative 1 over x squared, as you will. So pretty straightforward. We can do the same thing with implicit. I'll show you that, and then we'll kind of talk our way through it. So this would be a product rule. The derivative of the first is x. The derivative of x is 1. So I get 1 times y plus the first. And now the derivative of y, we could either write y prime or dy dx equals 0, since that's a constant. Then I'm going to rewrite this a little bit. Y equals, nope, sorry. Y plus x dy over dx. And really, we have to use kind of what we have before to plug in for y, if we can. So that's going to give me 1 over x plus x dy dx. And now I solve it for dy dx. So bring that over. I get x equals, nope, hang on. X dy dx equals negative 1 over x. Divide both sides by x. Sorry, running out of space. Dy over dx equals negative 1 over x squared. That was kind of messy. We'll find that some problems are easier to do this way. Sometimes they're easier to do explicitly. Some of them we can't do explicitly, so we have to use this formula. Okay, I can put that all on the screen at once. So remember from 2.6, I believe, we dealt with the chain rule. So we have the derivative of the outside function, leaving the inside as is, times the derivative of the inside. We're going to use the same idea over and over again for implicit differentiation. And so as I did above, every time you take the derivative of a y, you either write down y prime or dy dx. Honestly, when I'm doing this myself, I usually write y prime, but the primes can kind of disappear, so be cautious. And then our very last step, as I did for the one previously, is you solve for your dy dx. Okay, let's have a nice one to start. We'll get there. So find the derivative. I'm going to go in order. For the most part, this acts like a regular derivative problem. So the derivative of y cubed, I'm going to take 3y squared. I took the derivative of y, so times the inside, which is dy dx. Same deal for y squared. Bring it forward. 2y. We took the derivative with a y, dy dx. The derivative of negative 5y, negative 5 times dy dx. All right, anytime we take the derivative of x, we don't write dx dx because it's just 1, we just have it. So I get negative 2x equals 0. Don't forget our constants are zeros. I used to forget that. Okay, the worst is behind us, now just a little algebra. So I'm going to leave everything with the dy dx on the left side. Anything without goes to the right. Yeah, enough space. I'm trying not to skip too many steps. Add that to both sides. I'm going to factor out my dy dx. And I'm left with 3y squared plus 2y minus 5 equals 2x. Oh, barely have enough space. And you know what? We're going to go over here. Solve for dy dx. So divide both sides by the 3y squared, etc. So dy dx equals 2x all over 3y squared plus 2y minus 5. And we are done. So middle of the problem is honestly the same with the one extra step of adding the dy dx in there. Sorry, my message. And at the end, the worst part is just solving for said dy dx. Sometimes we can plug y back in and clean it up a little bit. In this case, we can't because we couldn't get y by itself. So we just leave it in terms of x and y, call it a day. Did I leave myself enough? Oh, I did. Look at that. I left myself enough space. All right. We're going to do the same thing. We have an ellipse here. So we're going to find the slope of the tangent line at root 2 and negative 1 over root 2. So first things first, derivative. I get 2x plus 8y dy dx equals 0. Now, the derivative's done. We could solve it for dy dx, or I could just plug things in and solve it that way. It's the same regardless of what we do. So I'm just going to plug it in. I get 2 times root 2 plus 8 times negative 1 over root 2 dy dx equals 0. Solve for dy dx. So subtract my 2 root 2. I get negative 8 over root 2 times my dy dx equals negative 2 root 2. And now I should have left myself a little more space, but we can scoot it over. There we go. I need to get rid of my -8 root 2. So I'm going to multiply both sides by the reciprocal. Y dx equals, okay. I'm going to come off to the side here. -2 root 2 times root 2 over -8. Root 2 times root 2 is +2. So I'll just keep going. -2 times 2 over -8. So 2 times 2 is -4 over -8, which is just 1/2. So dy dx equals 1/2. Excuse me. So hopefully it's not too much side work on that one. Just remember 2 root 2, the roots cancel if you multiply it by root 2. If you throw that in your calculator, just be careful where parentheses go and make sure you have the proper things outside of the radical. If not, it kind of blows up on you. Okay, come on screen. There we go. Okay. We have x minus y over x equals 2. You could do this one implicitly or explicitly. What do I want to do? It's the implicit chapter. Let's do this implicitly. So I'm going to rewrite this first off. I get x minus y times x to the -1 equals 2. This just makes doing the derivative a little more straightforward. So left to right, take the derivative of x, which is 1. We have a product rule. So the derivative of the first is 1 times dy dx times the second as is. Let's put this in parentheses. Plus the first times the derivative of the second. So -x to the -2. And that's done, equals 0. It's kind of gross. 1 minus, let's clean up, dy over dx times 1 over x. We're going to have a double negative, so we have y times -x, negative, so this gives me plus y over x squared equals 0. Excuse me. I'm going to move everything with the dy dx on one side, everything else on the other. In this case, I'm going to move the dy dx over to the right, so it's positive. And that's yuck. So multiply both sides by x. This gives me x plus y over x equals dy dx. And we could clean this up a little more, but I'm going to choose not to. Well, actually, so if I were to take my original function, you get x minus 2 equals y over x. I can plug this in right there. So it gives me x plus x minus 2 equals dy dx. 2x minus 2 equals dy dx, and we're done. I do not know where homework is going to ask you to do this. To be honest, if I were to look at this problem and I see that I can separate out the y, which means the nasty algebra will be at the front end of the problem instead of the end of the problem, the beginning instead of the end, I would probably solve this for y and do my thing. It makes the problem look a little nicer. Ideally, you want your equations to be as simple as possible before you take the derivative, which usually means doing some algebra from the start. But as always, it's up to you. So this last one, I have two more, don't I? Yes, two more. Okay, this guy we cannot separate out. We don't have any crazy fractions going on. Am I going to do that? No, we're going to leave it. Sorry, I was trying to decide if I wanted to rearrange it a little bit. I'm going to choose not to. All right. The derivative of a constant is 0. The derivative of 4y is 4 dy dx. The derivative of 3x squared is 6x. And I have a product rule. So plus the derivative of the first, 2x. I didn't take the derivative of y, so it stays. Plus, whoops, not 2x. X squared times dy dx. All right, everything with the dy dx goes on the left. Everything else is going on the right. So 4, no, that's fine. Minus x squared dy dx equals 6x plus 2xy. Factor out. And divide. Oh, I left myself enough space. I always misjudge the amount of space I need. Oh, and that's our derivative. So again, I could have separated this as whoops, because y was to the first power. I could have factored that out. But then I have a product or a quotient rule. And the quotient rules always get a little dicey, in my opinion. I would much rather do implicit with product rule than explicit with quotient rule. I'm not sure if we do this other really cool type of derivatives later called logarithmic, which makes things better, but it uses implicit as well. So it makes it a little nicer to deal with. Yeah, okay. I'm just making sure I did it right. Last one. I'm not going to do implicit. This, in my opinion, isn't worth it. So that is a fair assessment. If you look at a problem and you think a different method is easier, use the method that works better for you. Know how to do the others because sometimes you don't have a choice, but sometimes you do. All right, so I'm going to cross multiply, which gives me 4y equals x minus 3. Divide both sides by 4. I get y equals 1/4 x minus 3/4. This is a nice little derivative. dy over dx equals 1/4. The implicit would have been not a disaster, but nowhere near as nice. This is much easier to deal with. We're done, so we don't have to do anything more with that. All right, that is the end of my chapter 2 material. Chapter 3 is graph analysis. So we're going to take some graphs and figure out how to graph them a little nicer using calculus. I will put Desmos, a link to that online, so it'll help you look at the graph. Sometimes you want to reverse engineer things, so looking at the original graph versus what you're supposed to be doing, help you figure out how you're thinking about it, if you're thinking about it wrong, right, etc. But anyway, that is that. So I will post